Good, good morning, everybody. Today we, we have a seminar, a family seminar, and I I I have the pleasure to introduce you to Professor Stephen Aylward. Professor Aylward is an, an associate professor at University of North Carolina and also uh, a senior director at Kitware. Actually, Professor Aylward is the director of strategic initiative and founder of Kitware at, at North, North Carolina. So he's responsible for different innovative projects, both in University of Carolina and at, at Kitware. So thank you. Thank you again, Professor Stephen, for being here. And, please, when you're ready to start the presentation, please.
Thank you very much for the introduction, and I really appreciate the opportunity to be here and to present to you today. And so I will share my screen and begin the presentation. Okay, so today I'm going to be talking about the Medical Open Network for AI. It's an open source project that's been developed between King's College London and NVIDIA that has now a large community around it. But prior to talking about MONAI, I'm going to talk about the motivation behind MONAI, and that's really open science. Open science, I'm going to go into some detail of the history of it and positives and negatives in dealing with it. But really, it is a driving factor in so much of what we do nowadays. And MONAI and open science are also two passions that I have. So I really do welcome this opportunity to speak with you. MONAI and open science are very interleaved with one another. And I think it will have great potential within your research labs in academia and industry, your Ph.D. dissertations, and really the future of medical imaging in general. So this is you. Maybe you're going to be a professor, maybe you are a professor, maybe you're just going to work for a company and lead a research lab, or you're going to lead your coworkers in meetings, whatever the case might be, this is you. And then these are your students, all right? And so work with me here. These are collection students that you have, or else they're coworkers that you have while you're off in industry, or the research lab that you lead. And then within those, there's Bob, and Bob is the perfect student. Bob can do no wrong. Bob is a great programmer. He's a great researcher. He runs, the infrastructure of your research labs. He helps everyone with their coding. He really is the perfect student, the perfect employee with you. But then one day, tragedy strikes. and Bob graduates, or Bob leaves to go to another company, something happens, Bob is no longer part of your team. And then you see the inevitable issues arrive. I cannot find Bob's code. Bob's code won't compile. I can't replicate Bob's results, or I emailed Bob a question, but he hasn't responded. All right. We've all seen this. All the research, all the help that Bob had given to everyone along the way. When Bob left, he took that knowledge, that expertise, those capabilities with him. They weren't preserved. The answer to this issue is open science. And so when thinking about open science, don't think about everything being open and shared, but thinking about addressing the issue of how to have your work preserved. So whether it's shared with coworkers or shared with the world, it's preserving your work so that it can move forward. And this is not a new idea by any means. Descartes in 1637 published a discourse on the method, which is the scientific method or experimental method. And in that discourse, he said, doubt everything and only believe those things that are evidently true, those things that are reproducible. And that is the heart of open science. You want it so that other people can replicate your results, so that when you go off and get a job, or when your employees or your students go off and get a job, you can continue their work. You can build on it and advance the state of the art. So open source is reproducible science. And what that means nowadays is it's boiled down to essentially three things: open source code, sharing your data, and then documenting your processes and results so that others can fully replicate your work. Open source is now easier than ever before, all right? And what open source means is really thinking about coding for others. Sure, it does mean using a license that's an open source license, such as Apache, BSD, MIT, whatever license. But it really means coding for others. So it's writing readable code, it's making it so that your code is commented, and it's keeping it simple. It's not writing overly complex code. And I find this coding for others also even applies for yourself. If you write code, if you document what you're doing, it helps me 6 months, 9 months, a year later when I return to that research, pick up where I left off. So this is just very good practice. And the mantra that we repeat is coding for others when doing this open source code. And it's easier than ever before because of GitHub. GitHub has revision control. There's other systems out there that provide revision control. It allows you to advertise your work because it's indexed by Google. So if you put a good README in there, people are going to find your work. And so not only will it have an open license, but it'll be easily discovered. And there's a lot of support for running an open source community on GitHub and other platforms so that people can register issues and you can address them and so forth. And so it really, when thinking about open source code, it's not just the license, it's everything that goes around and into that open source code. And when they're talking about sharing data and publishing, that's also easier now than ever before. That's open access data, such as grandchallenges.org is a wonderful repository of data that's been contributed to a variety of grand challenges in medical imaging and medical medicine in general. And so that data is there for you to use and incorporate into your work. And you can also contribute data to the system at grandchallenge.org. And then there's the ImageNet archive, the Cancer Imaging Archive from the NIH, so forth and so on. So using and contributing to open access data is easier than ever before. And also creating open access publications. I'm not saying don't do traditional journal publications and everything, but simultaneously, IEEE and a bunch of these foundations, SPIE and so forth, are allowing you to also publish your paper on Archive or ResearchGate or your own website so that others can access it more easily. And so all of these things, the sharing of data and publications, the writing open source code, combine together to make open source, open science possible, reproducible research possible. But there are still challenges with this. It's not, it sounds like a great idea, but you have to admit there's a sense of competition in science, all right? So, you don't want to have to be the person reinventing the wheel, but generally you think you can make a better wheel than someone else. And this is not only inherent in what we do, but it's also a learned thing. In classrooms, when taking exams and so forth, that sense of competition exists within academia and it persists through the research that we do. And so this is something that needs to be overcome in order for open science to really take hold and have impact. Second thing that there is of the three challenges for open science, the second one is inadequacy of journal articles. So when trying to replicate someone's results, we've all seen this and we've all experienced this when writing these journal articles ourselves. Stuff gets left out of the journal article. The complexity of a research lab is extremely difficult to condense down into an 8-page journal article. And so replication of results is not possible there. But now we can publish code with it and so forth. And so it's not the complete solution, but for a very long time, it's been thought of as a complete solution. We need to move beyond that mentality. And then there's also a matter of priorities. Sure, open source and open science sounds like an awesome idea, but I'd much rather spend my time publishing papers, finishing my dissertation, writing a grant proposal, starting a company, selling my company, and in general, making $1 million, right? And so this is all the excuses that seem like better priorities, and they seem like they would be something that is incompatible with open source and open science in many ways. But what I want to argue is that the benefits of open science outweigh the costs, and some of those costs are actually benefits in themselves. So when talking about funding, so saying that you would rather pursue funding than releasing your code as open source, releasing code of open source is part of a grant proposal and discussing how in that grant proposal, you're going to take that open source, you're going to take your research and make it replicable, get it out there so it has a broader impact. That's a wonderful way when reviewers look at your work for an academic review, or also a lot of times within companies, within corporate reviews as well. That brings in more funding. That adds value, recognized value to the work that you do, so it has the broadest impact possible. From the NIH, we have a $3.4 million grant to continue the development of one of Kitware's software products, open source software systems called VTK, the Visualization Toolkit. This is wonderful funding that is really going straight to open source development. And so it's a wonderful way to actually get funding. It's not in competition with funding. And also, if you look at for the Visualization Toolkit, they had 2 different papers that were published, one by Will Schroeder, the other one by Bill Lorenzen. And when people use VTK, we ask them to cite these 2 publications, these 2 journal articles. Well, if you look at these 2 journal articles combined, they now have over 13,000 citations. So if you want to get tenure, if you want to work on your publications and you want your publications to get cited, release the software that goes with that. Just as we did with VTK going with these 2 publications, 13,000 citations is something anyone would love to have in their resume, in their CV, and their tenure application. And then we also can talk about impact. A lot of people get a lot of satisfaction from their work having the broadest distribution so that it can be picked up by others and incorporated into multiple products. It can really change lives, save lives, approach and solve global healthcare issues, and so forth. And that's done by releasing things open source. If you look at our software, a couple of the packages that Kitware releases, open source, freely available, we have CMake, VTK, ParaView, 3D Slicer, and ITK. Those are 5 of the ones that we release. They have, in combination, over 150,000 downloads per month. This is just phenomenal, the impact that these are having. And actually, there's more downloads than this at this point. The slide's a little bit old. But getting this worldwide impact for your work is extremely satisfying and motivation. It's a value for quite a few people. And what's more important is also the realization that if you don't practice open science, not only is Bob leaving a tragedy, but if you don't practice open science and publish your results only as a journal article, there's a lot of risk to actually doing potentially harm rather than good. And so a documented example of this was a paper that was published in Nature in 2012 by the 2 gentlemen shown on this slide, really heads of research in both industry and academia. And what they wanted to do was replicate the results from landmark publications in the field of radiation oncology. Now, as landmark publications, these publications were actually driving how radiation oncology was being applied. They were impacting the treatment of patients. And so protocols for radiation therapy and chemotherapy and so forth were driven by these publications. And so clinical practice was defined by them. And so they're like, well, we want to advance the field within these areas. They identified these 53 papers, and then they sought to replicate the results so that they could then extend them and build upon these landmark papers. But what ultimately they found was that 47 of the 53 results in these landmark publications that were impacting patient care, they could not be replicated. Not saying anything malicious was going on by any part of the authors or anything along those lines, but it feeds back to the fact that the inadequacy of a journal article to capture the complexity of what goes on within a research lab. And so, again, nothing malicious, but the inadequacy of journal articles alone to replicate results. If Bob leads, that's a tragedy, but actually if your publication ends up driving healthcare, which we would all love to do, it better be reproducible. And so, again, open science is such a major importance throughout experimental science, but in particular for medicine. And I also think that why is deep learning succeeding? And now I'm moving on to the MONAI topic. So what does this mean for MONAI and our other efforts? Well, actually, I believe that deep learning is succeeding this time around. So deep learning, our neural networks were around since the 1980s, 1990s. They're really taking off this time. I would say it's definitely because of the recognized performance, the capabilities of these neural networks with the additional deep layers and improved transfer functions and so forth. They're phenomenal performance. But even more so, deep learning has fully embraced the concept of open science. If you want to apply deep learning to your problems, there's PyTorch, Keras, TensorFlow, a variety of different options that are freely available, open source toolkits for you to really apply state-of-the-art deep learning algorithms to your data. And so it's a phenomenal and often unrecognized aspect of this deep learning revolution that's occurring. And that is really what developed or led to the development of MONAI. And so when I talk about deep learning success and performance, what exactly do I mean for the performance of deep learning systems? Well, I'm going to leave that as an exercise to the audience. Right? We have all seen the multiple stories within the medical field of COVID being detected from ultrasound and CT scans of patients using AI and deep learning methods. We've seen improved surgical guidance systems. We've seen identification of new diseases because of the investigations provided by deep learning and AI systems. And then when I talk about deep learning success being due to open science, we see this by the massive number of papers that appear in Archive before they appear in the NeuroITS conference or any of these deep learning conferences. So Archive has become a respected venue for the publication of state-of-the-art deep learning results, and it's freely available, all publications there. Additionally, NIH and other EU, European Union agencies have mandated that any work research that you do that results in a publication, that publication has to be open access. So policy changes as well as venues have been phenomenal for open science in the deep learning field. There's also wonderful deep learning data sets out there, ImageNet and the Cancer Imaging Archive. There's algorithms, as I mentioned, PyTorch, and it led to MONAI. And then there's even platforms where you can run your algorithms for free, such as Google Colab, that has NVIDIA processing units that you can take advantage of for free on their systems. And so all of this, like I said, led to the Medical Open Network for AI. We realized that there were some outstanding tools there already in existence. However, we wanted to focus on medical imaging. And so the goal of MONAI was to accelerate the pace of research and development by providing a common software foundation and a vibrant community for medical imaging deep learning. Again, it wasn't just about the software, but it's also about building that community. It's about the documentation, the support, sharing of data, and so forth. It began as a collaboration between NVIDIA and King's College London. It's freely available. It's based on PyTorch, so we didn't try to come up with something completely new, but we enhanced the capabilities of an already existing and very successful toolkit. And it prioritizes reproducibility, because in medical imaging, that is so very important, more so almost than any other field. And so, again, just as we built upon PyTorch, the spirit of open source community is not that you go off and build your own thing and release it open source, but you also contribute to open source that's great, that already exists. And so across the bottom, we see toolkits that already exist that we're trying to apply deep learning to medical imaging. And there was NiftyNet, Deep Neuro, DLTK, Pretrained, and these are from industries such as NVIDIA, as well as KCL, German Cancer Research Center, and so forth. They all had their own toolkits. And so instead of competing with this, we invited them to join us. We invited them to join the Kitware NVIDIA King's College London effort on the development of MONAI. And MONAI focused really on the core where reproducibility was most important, such as data augmentation, neural network definitions, loss functions, and validation methods. And that's where MONAI focused its effort so that it could be used with a variety of other toolkits that already existed for managing data or publishing evaluations on dashboards and so forth. And so MONAI is an integration. It's a bringing together of the communities that already existed in order to form a much more cohesive and synergistic community that was based on open source in this common platform. Why is MONAI needed? Why not just keep using PyTorch? Well, biomedical applications have specific requirements. Imaging modalities are not like computer vision 2D PNG modalities. You have MR, CT, ultrasounds, and so forth. And each of these have their own special characteristics associated with them. For example, CT has Hounsfield units, and that needs to be understood. MRIs have TR and TE times, and those need to be understood. All of that is very medical specific. Additionally, those data aren't delivered as PNG images, but they're delivered as DICOM images, and that's a format with hundreds of tags that needs very specific loaders and writers in order to deal with it. And then we have to consider things such as the physical voxel spacing, the point spread functions that was used to acquire the data, and that is completely absent from PyTorch and the other computer vision deep learning methods. And then there are certain network architectures that have already proven themselves to be very good with medical images that aren't necessarily as widely popular as generally applicable to other domains. And so all of these things are bundled together within the MONAI system. And then they're wrapped so that they address the specific needs within the medical field, such as sample size limitations, annotations, uncertainties, and so forth. So a lot of theory also is wrapped around all of these technical capabilities that are listed above. But most importantly, MONAI emphasizes reproducibility. So one way of emphasizing reproducibility is we make it so that if you adopt MONAI, and the more people that use MONAI, the more people are standing on the shoulders of giants, is what I say. The more people get to take advantage of the work that other people have done that are really some of the top people within the field. So they don't have to go out and reduce their own random reorientation or GPU accelerated transforms and so forth. Those are already within MONAI. So it reduces the amount of re-implementation that has to be done. It allows you to focus on what research you want to do. And we provide baseline implementations so that if you do your research, we have a baseline against which you can compare your research, and it's available within the MONAI toolkit. And then it demonstrates best practices. And what I mean here is it demonstrates open science practices and how to share data, how to publish results, and so forth. And MONAI has really taken off. This open source software on top of PyTorch now has 74 people constantly watching it. We have nearly 2,000 stars on GitHub, which is phenomenal, considering we're at the 0.5 release. We just released it in April of last year, so within a year, 2,000 stars, which puts it in, in the clouds of GitHub, and 350 forks. We have contributors from 58 individual contributors, really from around the world. It's getting to the point where a significant portion of the toolkit was not written by King's College London or NVIDIA or other folks. It's written by the community and contributed back to the toolkit. So not only are they finding bugs, but they're contributing outstanding algorithms to expand its capabilities. So, and then with all of these wonderful contributions, we've also had wonderful adoption. We held a boot camp last year in which we thought we would maybe get about 60 people to attend, and we opened it up for people to apply to attend. Well, we ended up with 563 applications for these 60 positions in the boot camp. We were on MONAI version 0.3. It was really early on the process. But there was such a community interest and support and desire to have this that it absolutely exploded. We had 40 different countries represented during that initial boot camp in October of last year. And what we did was we ran a challenge to find out who came up with the best solution for some problems that we posted. And it ends up that people in Ethiopia were the ones who generated the best solution. And I think that's wonderful because chances of engaging them in an in-person, event would have been challenging. But by having this as a virtual event, participants from around the world generating so much interest that really we get to have every company shine and excel and do their best in this boot camp. And so you might be thinking that MONAI, wow, this thing must be complex. What I'm going to show in the next couple of slides, it's very easy to use. So to install MONAI, and listen, this is all very well documented on the website. So if these slides, I'll make them publicly available after this presentation. But realize the monai.io website has much more detail. But it boils down to the simplest command for installing Python modules, and that's a pip install MONAI. And then you can import MONAI and ask it to print out its configuration. And when you install MONAI, it actually installs an environment with a bunch of other packages that work together in order to create a good medical imaging research environment within Python on your machine. And then looking at some of the neural networks that are out there, one of the most popular ones that is used in the medical field, it was first published at NICI a few years ago. It's known as the UNet. And so if you want to do UNet and PyTorch or some of these other frameworks, you actually, it's illustrated in the upper right-hand corner, and another similar form of illustration is just below that. Multiple layers that exist with this. There's convolution layers and all these different things. And to specify all those manually is a bit challenging, especially, errors creep in and they're really hard to debug within deep learning systems. But because UNet is so popular, MONAI provides a single function call in order to specify your UNet architecture. And that function call is there. In this function call, it's specifying that you're working with a two-dimensional image as opposed to a three-dimensional images, but 2 or 3-dimensional images are supported. There's going to be one channel, so it's going to be a grayscale image that's inputted, but we also support RGB images, or else you can have MRI, CT, and multiple channels, multiple images from the same person all input simultaneously to this UNet. It's going to have one channel of output, and that output will be like a segmentation of the liver or the spleen or whatever you have training data to show it. And then there's this notion of channels and strides, which are specific to the UNet. But by specifying those 5 values, you actually completely specify the remainder of the architecture, what's happening internally. And so it really simplifies the definition of this UNet. And sample UNets are given for spleen segmentation within MONAI for other clinical tasks. So it's easy to build upon this work. And then, so open source code, there it is, reproducible, very easy to use, but also it gives you open access to medical data. What I want you to note here is the second line in this system, in this insert, which shows decathlon dataset. Decathlon dataset was one of the datasets from grandchallenge.org. It's a dataset that exists out there that's publicly available, one of 10 datasets. And in this particular case, case number 5, it did prostate segmentation, but it did segmentation of other organs in these 10 different challenges. Well, we made it so that if you want to develop a new method and participate in that challenge, you actually, again, just have to do a function call. And what it does in that function call, you specify your root directory where you should download the data from. You specify which of the tasks of the decathlons you want to participate in, and whether you want the training or the testing data. And are you going to perform any transforms or modifications to that data as it gets read in, and should it be downloaded if it doesn't already exist on your system? Well, if you go ahead and issue this one function call, the output is shown below. What it does is it goes out, grabs that data from grandchallenge.org, downloads it to your computer, runs an MT5 checksum verification that the proper data was downloaded, that there weren't any errors during download, and then it uncompresses the data, and it makes it available for processing by a MONAI network, all via this dataset variable, which is returned from this function call. And so what this is doing is promoting reproducible results. So reproducible results at first depend upon having consistent data as input. And so this ensures that you have very consistent data that is being used by you and everyone else within this challenge. The exact same training data is being used. Errors didn't happen within that. And so your results, if it's better than someone else, we know that it's probably better than someone else's. And so the field can advance more rapidly. And then, so we have open source data for defining a UNet. We have open source system for defining a UNet. We have open access to data. Now, if you just put all that together, 10 lines of code will have you a MONAI operating trainable neural network. And looking through these 10 lines of code, we specify transforms, the fact that we want to, and this is standard built upon PyTorch standards for those who know it, where we specify the transforms, how the data should be manipulated as it's read from this repository. So as it's read from the grandchallenge.org. And in this case, so this is how the data is going to be transformed. And what this is specifying is that we're going to normalize the data as it's read in, so that it has values between 0 and 1, and we're going to convert it to tensors for processing by MONAI. The data set we're going to use this time is the MedNIST data set, which is another standard data set at grandchallenge.org. It's going to be downloaded, just the training data. And then we're going to do a supervised trainer using the DenseNet, neural network as opposed to the UNet neural network, and its arguments are specified. And we're going to use the atom optimizer, a cross entropy loss function, and then a simple infer. And then the very last line is to run your trainer. There's multiple examples and detailed description of what's going on here within the MONAI.io. But this is showing that all this deep learning that's occurring out there, because we're able to come up with the MONAI toolkit that's so focused on medical applications, optimized for it, it made it much easier. 10 lines of code. You're running DenseNet 121, or you could substitute in a UNet or so forth in order to train your data that's out there or participate in a challenge. And that simple example is really just scratching the surface of what MONAI can do. MONAI can do what's also known as federated learning. This is one of the advanced capabilities that it has. And federated learning is where you train a neural network partially using the data at one hospital by shipping the network to that hospital. And so the data never needs to leave that hospital. What you get back, then you can ship to another hospital and they continue the training process using their data. And then you ship it to another hospital. And all of the results from those different hospitals, all the learning from those different hospitals are integrated in various ways. So you've distributed learning is occurring while protected health information from your patients is preserved at the hospital. It never needs to come back to you. And so this level of complexity, setting up these networks and exchanging the networks to these federated participants in this federated learning system, it's a pretty complex process. But again, we've tried to make it as simple as possible within MONAI. So MONAI isn't just about small research projects, but big research projects as well. And extensive documentation make this possible, wonderful web-based documentation for it. And also, it's been integrated with NVIDIA Clara, which helps you integrate into a clinical research environment. And so if you look at that workflow, that's the arrow across the top, you see you begin with the PAC systems, then you have the Clara system takes over and does interoperability. It packages the data in such a way for a particular patient so that it can be fed into the MONAI network. The MONAI network's results are then produced, converted back to DICOM, and then sent to a PACS. And NVIDIA's Clara system makes all of this possible. And NVIDIA Clara system also comes bundled with neural networks that already segment lungs from CT, livers from CT and MR, so forth and so on. So it's got about 20 different pre-trained neural networks that you can build upon in order to get your neural network within a clinical environment. And so again, open access to data. This includes easy access to data within a clinical system that we've enabled. And then people are using this. Again, I talked about COVID segmentation, spleen segmentation. These notebooks are available with the NVIDIA, with the MONAI system, and you can run these on Google's Colab environment for free, just to see what the results are like and to build upon them. And so it's a wonderful variety of demonstration applications that show you best practices for building your neural network and using them to solve clinical problems. And here's a variety of links that you can look at in order to learn more and then also contribute to MONAI. So not just use it, but contribute back to MONAI. Again, it's a community, and it's a community is supporting as well as using MONAI. So in conclusion, don't try to reinvent the wheel. Don't go out there and just say, you know, PyTorch is good enough. I'm just going to use PyTorch for my medical problem. As soon as you begin in PyTorch, it's a wonderful way of starting. But next thing you know, you want to work with more closely with clinical collaborators. You want to go out there and start importing DICOM images, or you want to visualize your results in 3D, so forth and so on. All of that is built into the MONAI system. So visualization capabilities through IPK widgets and so forth. So participate rather than compete. Don't be the guys trying to build your own wheel, and practice open science, not just in the broad, scary sense, but also within your own labs. And then who knows, maybe you'll end up making $1 million. So thank you very much for your time. That concludes my presentation. And I apologize.
Professor, your microphone.
Okay, thank you. Dr. Murtha, you are muted.
I'll give him a call.
Yeah. Dr. Murtha, you're muted. We cannot hear you.
Now you hear me?
Now we hear you. There we go.
So thank you. Thank you very much for the great presentation. Indeed, it's a very interesting concept, the open science and MONAI project. So, I wonder if the people in the audience had any questions.
Yeah, I welcome questions.
Yes.
Let's see. How was it done to manage / control the entire computational load with the large data set, given the giant number of hypererrors and the apparent high risk of overfitting? That is a wonderful question, and that is kind of the heart of research of deep learning. And so, look, managing the entire computational load is something that MONAI does well, because you can use, it supports not only GPUs, but multiple GPUs. So if you have a system with multiple GPUs, then it is able to expand its computational load, or spread its computational load across those multiple GPUs. And so multi-GPU capabilities are inherently built into the system and can deal with that large data set. It's still, you know, taking days to train is not unheard of for a deep learning system by any means. And so there's still high demand, but at least we'll maximize the use of hardware resources that are available. And given the high number of hyperparameters and high risk of overfitting, that is one of the grand challenges that exists within the deep learning environment. It is balanced between having a validation set, which is used in order to stop our testing set and validation set. The testing set is used to actually stop training before overfitting is detected. So you train using your training data and intermittently test using your testing data. And when the error starts going up on your testing data, you halt on that. However, you know, there's this whole area of ethical AI that you're touching upon here. Overfitting occurs within your specific data set. all right, for a specific training data set. And that's really high risk. I mean, we've got ways that we're starting to be able to address that. However, even more so, making sure your data set is representative of your population, that is absolutely critical, and ethical AI is beginning to address that. And that's where that includes explainable AI, where you find out what is driving the decision for the particular medical image that it's looking at. I saw some of the early neural networks that were out there, for example, and they were trained on images to recognize dogs and cats from the internet. And so the system did a great job of identifying dogs and cats. But when this GradCam, a way of identifying what was driving the decision for identifying dogs versus cat, once someone invented that technique and they applied it to these neural networks that could identify dogs from cats posted on the internet, well, it ends up that it would also look for, this GradCam system revealed that the neural network was looking to see whether or not there was a windowsill within the image. It wasn't just looking at the animal in the image, but it was looking to see if there's a windowsill, because it ends up that cats are more often on windowsills than dogs. And so this cat versus dog decision was actually being made not only by the features of the animal, but by the features in the surrounding image. And think about that in the medical domain. In the medical domain, there's some examples that we've seen is survivability of COVID, when this GradCam was applied to that. So people came up with ways of looking at CT scans and predicting whether or not someone would survive COVID. Well, it ends up that the scanner was looking for, I'm tapping myself, I have a pacemaker. The scanner was looking, or the neural network was looking to see whether or not a pacemaker existed within the CT scan or the wires of the pacemaker. And if you had a pacemaker and you were in this data set, they gave you much lower odds of surviving, all right? When maybe that shouldn't have been, it's a bias that's being incorporated, maybe or maybe not, on whether or not that should have been involved in that clinical decision. They thought the neural network was only looking at the lungs, but it ends up that it was looking at other features. So overfitting occurs in many forms, and it's a wonderful challenge that I think is going to come to a head within the next year in the medical field. Does MONAI offer pre-trained nets ready to be used in transfer of learning strategy? So MONAI comes with scripts for training the networks, but it's the Clara system, which comes with a variety of pre-trained networks. And so Clara uses MONAI, and it adds on to MONAI these 20 or so. I don't know. I apologize. I don't know. It was 20, but then they switched to MONAI, and I don't know how many they've retrained. But ultimately, there will be 20 pre-trained neural networks packaged with the Clara train system for lung CT segmentation, liver segmentation, and so forth. But MONAI is focused strictly on the source code right now. How does MONAI prevent the modules not working when there are different releases of toolkit versions or even an update of the MONAI code? Jessica, that is a great concern. And so you bring up a wonderful question. I'm laughing because we just came out with a new release, the 0.5 release of MONAI a couple of weeks ago. And it is the 0.5. We're hoping by November of this year to have the 1.0 release. And with the 1.0 release, we're going to have a stable API to MONAI. But right now it is a research toolkit, or it's an in development toolkit. And so the API changes. And so your code that worked with 0.4 might have to be updated to work with the 0.5 release. However, that's the plan, all right? The plan is to allow this breaking of backward compatibility today. But in November, when we have that 1.0 release and moving forward from there, it's going to be a very solid API that does not change. Except for every other major release. So once every 2 years there might be some API changes. And as far as the tools that it depends upon, if you pip install MONAI, we're very careful. Every night we have continuous integration tests where we specify for each of those machines what version of all the supporting, NumPy, Python, and so forth should be used by that machine to test compatibility of MONAI. And so we try to lock down specific versions of NumPy and NiBabble and so forth. So federated learning systems seem very good to mitigate privacy concerns on medical data. Is there any expectation when it will be available, or is it ready to use? It actually is ready to use now. And there's publications on federated learning using MONAI out of Stanford. Daniel Rubin, R-U-B-I-N, is the author of those, as well as at MGH, Jayshree, she has publications on that. And they show a federated learning system where it was MGH and Stanford, and I think one or two other hospitals, using a federated library, and I forget which one they used, but they used a federated library with MONAI in order to do this distributed learning. And so it's a hot area of research, but there's actually practical solutions now for doing this. They're not easy to do, not easy to set up, but there's very specific examples and wonderful people happy to help you in getting them set up.
One more question.
In training these models, how do you know how much data augmentation is appropriate? So you don't, all right? So experimentation is important. However, what they're finding is that it's both more critical and less critical than what you would expect. So there's general guidelines that are provided by the example code as far as different augmentations that are out there. And what people are finding, though, is that you can change a neural network architecture and you can change an augmentation strategy quite a bit and get similar results. All right, so it doesn't impact the results. But when I say similar results, that's the downside, because if you train a neural network using the exact same data and the exact same augmentation, but starting from a different random initial condition for the weights in the neural network, you'll get very different results, potentially. And so a neural network with a particular augmentation gives you a cluster of results. All right, and typically people train the networks multiple times from different random initial conditions and then pick the best one of the 10 or 20 that they trained, even though it's all the exact same architecture. They pick the best one, and that's the one that they publish and use. And so it ends up that you can change the neural network architecture and you can change the augmentation and the data a fair amount, and you'll still maintain within that cluster. So it's a research topic, though. And look at few shot and one shot techniques that are coming out of computer vision, such as YOLO, for training, giving very limited data. Thank you.
Thank you, TV. Actually, I have one question for you.
Oh, thank you.
My question is very simple and perhaps maybe is there any minimal requirement for the hardware in order to MONAI work?
Yeah, so as far as the minimum hardware requirements, it does support CPU-based training, but in part as much as PyTorch does, but it's very, very slow. You will want to have a GPU within it. I actually am presenting on a laptop that has a 10 NVIDIA GeForce 1650, I think. And so this is a Dell laptop that's 2-3 years old, and it will run MONAI and train the spleen example and a variety of different examples pretty well. It takes, an hour, but it's able to achieve that. So that's a laptop with just an NVIDIA chip within it. If you go out and get one of the RTX or one of the newest NVIDIA processors that run anywhere from $300 to $1,000 and more, you have a very good system for training a network locally. Now, what I often do, though, is use Colab from Google. And Colab is Jupyter notebooks running in a web page using Google hardware. And it actually has GPU capabilities, and even on the free tier. But if you pay, you can actually get access to, and NVIDIA has a cloud. So these are just like AWS, Google, NVIDIA. They all have cloud services. And often, because the GPU hardware is advancing so rapidly, I think it's often more cost effective to not buy the hardware yourself, but to use the cloud systems that are out there so that you can keep up, after a year or two, your hardware is not obsolete. So I recommend, if you go to monai.io, our website, and scroll down, there's a link to a Google Colab running the spleen segmentation. And when you go to and follow that link and go to Google Colab, you actually can create your own copy of that script and start modifying it, sending different data to it and so forth. And so it's really, if you want to experiment, that's what I recommend, is using some of the free cloud resources rather than trying to buy the minimum system. Because, what people tend to buy are, big towers with 3 and 4 GPUs within them that get quite expensive. So.
Okay, Steven. Thank you very much again for the presentation. It's a really interesting project. The MONAI and also really important concept, the open science. So congratulations for this. Thank you.
Oh, well, thank you very much. Really appreciate it. So, and please, my email is steven.aylward@kitware.com. Feel free to email me your questions that you may have and follow up. And I really enjoyed this opportunity. Thank you.